Let us go over gas stoichiometry. And in here, we're going to understand balance equations that have to do with gases and how we're able to calculate moles, volume, and other things that we're able to calculate from balanced equations. Now, let's say we have got one mole of a gas, and this one mole of a gas, and when we're talking about gases in this case, we're going to be talking about an ideal gas because a real gas might not necessarily get to obey all these gas laws that we get to discuss, like the Bohr's law, the Charles law. So we get to discuss an ideal gas. So when you have got one mole of a gas at 0 degrees, now we know that 0 degrees is the same as 273 Kelvin. And let's say now this same gas is also having a pressure or at a pressure of 1 atmosphere. So we can be able to determine the volume of this one from the combined gas law, that is PV is equal to nRT. So the pressure in this case we can see that is 1 atmosphere multiplied by the volume, that should be equal to the number of moles, right? So since we're talking about one mole and then multiplied by the universal gas constant, which is 0.08206, that's the one we're going to use depending on the unit for pressure, volume, and the temperature units that we have, and then multiplied by the temperature. Now we always use temperature in Kelvin in this equation. So to find this volume is going to give you 22.42 liters. So this volume that we're able to see here is the volume of a gas at standard temperature and pressure, STP. So we need to know that the volume of a gas at standard temperature and pressure is 22.42 liters. So this is the one we are going to be working with even other uh, substances, like just other gases. So let's say as long as you have got one more of a gas, okay, let's say we have got one more of oxygen gas at standard temperature and pressure. This is going to give us 22.42 liters. Whether it is one more of oxygen or one more of sulfur, one more of ammonia, as long as it is standard temperature and pressure, we are going to have the same volume here. Alright, let's consider this example. Sample of nitrogen gas has a volume of 1.75 liters at standard temperature and pressure. How many moles of nitrogen are present? Now, we already know that one mole of any gas at standard temperature and pressure is supposed to give us 22.42 liters. Now, how about the 1.75 liters? How many moles is it going to give us? So the number of moles therefore is going to be 1.75 divided by 22.42, and that is going to give us 7.81 multiplied by 10 to the power negative 2 moles. So these are going to be the moles. The next one, quicklime, which is calcium oxide, is produced by thermal decomposition of calcium carbonate. Calculate the volume of carbon dioxide at standard temperature and pressure produced from the decomposition of 1.52 grams of calcium carbonate. So the first thing we need to understand the balanced equation of this reaction, which is here. We can see if we decompose one mole of calcium carbonate, we're going to produce one mole of quicklime and one mole of carbon dioxide. Now what do you want to calculate? Calculate the volume of carbon dioxide. So we want to calculate the volume of carbon dioxide. Okay, from the decomposition of 1.5 grams of calcium carbonate. So let's first understand the number of moles of calcium carbonate which were decomposed, and that is given by mass over molar mass. The mass of calcium carbonate decomposed is 1.52. The molar mass of calcium carbonate is 100 grams per mole. That is going to give us about 1.52 moles of calcium carbonate. From the balance equation, we can see that number of moles of carbon dioxide is equal to the number of moles of calcium carbonate because they are in a ratio of 1 to 1, and that is going to be equal to 1.52. Now that we know the number of moles of calcium carbon dioxide which were produced, we can determine the volume of the gas produced. So we know that one mole of gas, since this is supposed to be at standard temperature and pressure, we know that one mole produces 22.42 liters. So now we have got 1.52 moles. Want to see the volume that is going to be produced. So the volume is going to be 1.52 multiplied by 22.42 liters. So therefore that is going to give us 34.1 liters of carbon dioxide to be produced. The next one, a sample of methane gas having a volume of 2.8 liters at 25 degrees Celsius and 1.65 atmosphere was mixed with a sample of oxygen. So I've got methane, which is CH4, right? That is mixed with a sample of oxygen gas. And this gas, what are we going to produce? So when we get to react, an alkane with oxygen is going to be decomposed, and the reaction produces carbon dioxide and water. Right. So we need to know the balance equation from here. To balance it, we are going to put a 2 here. We are also going to put a 2 here. So the reaction is now balanced. Now from what we've been given, we've been told to say 2.8 liters at 25 degrees and the pressure of 1.65 atmosphere was mixed with a sample fraction having a volume of 35 liters. Now the temperature is different at 31 degrees Celsius and the pressure is also different, that is 1.25 atmosphere. So the mixture was ignited to form carbon dioxide and water. Calculate the volume of carbon dioxide formed at a pressure of 2.5 atmosphere and temperature of 125. So the first thing, let's determine the number of moles of methane and the number of moles of oxygen which reacted. Okay, so the number of moles of methane present, how are we going to be able to determine that? From the gas law, we know that pressure times volume is equal to number of moles times the universal gas constant times temperature. So if we make n subject the formula, we're going to have PV over RT. So therefore this is going to give us pressure. We can see the pressure given is 1.65 atmosphere multiplied by the volume, which is 2.8 liters, and we are going to get to divide that by the universal gas constant, which is 0.08206 multiplied by the temperature. Now the temperature is 25 degrees. We always use the temperature which is in Kelvin, and that is going to be what? Just add to 25 to 73. That is going to give us 298. So therefore the number of moles that we're going to determine is 0.189 moles. We also determine the number of moles of oxygen. So number of moles of oxygen is going to be equal to, we also do the same, pressure times volume over RT. Now I can divide by the coefficient 2 there, right? But I can first just do this. So pressure now for oxygen, we can see that is 1.25. The volume for oxygen is 35, and then we're going to divide that universal gas constant 0.08206, and then multiply by the temperature. The temperature for oxygen is 31, so add 273, we are going to get 304. So this is going to give us 1.75 moles of oxygen. Now because I've got a coefficient of 2 here, I'm going to divide these moles by the coefficient of 2. So I'm going to divide by 2. Our aim, because we want to find the volume of carbon dioxide produced, I need first to determine which one of these two is the limiting reagent, and that is the one we are going to use to determine the moles of carbon dioxide produced. 1.75 divided by 2, that is given us 0.875 moles. So from the reaction we can see these are the moles of ammonia which are reacting with these moles of oxygen. So the smaller one is the one which is going to be used up first, and so it's the limiting one. So you can see that this value is much smaller. So this tells us that ammonia in this reaction is a limiting reagent. So we're going to use ammonia to find how much of product is formed. Take note of the number of moles of ammonia, which is 0.189. So the number of moles of ammonia is equal to the number of moles of carbon dioxide produced, and that is going to be equal, because the mole ratio is 1 to 1, and that is equal to what? 0.189, which we've already determined moles. Now we can determine the volume of carbon dioxide, and we've been told at a pressure of 2.5 atm and temperature of 125. So how are we able to determine that? From the ideal gas law, we know that PV is equal to nRT. So the pressure in this case, they've told us at a pressure of 2.50 multiplied by volume, that will be equal to the number of moles, 0.189, universal gas constant 0.08206, and then the temperature is 125. So compare that to Kelvin by adding 273, 125 plus 273. That is going to give us 399. So divide both sides by 2.50. So therefore the volume of carbon dioxide to be produced is going to be 2.47 liters. So that is it for this one.